welcome back. So today we're going to talk about a very broad topic called light. For many centuries, probably millennia, scientists and everyone has wondered, what is light? It is a very good question to ask yourself, because even though we all see light, we don't know what it's made of. We just know we can feel it as heat, and then it lights everything around us. So this question of what is light has guided physicists for ages to try to discover what it is. The first important answer that we're going to talk about was given by Isaac Newton in 1704. And Newton proposed that light was made of really tiny particles called corpuscles. So his theory is called the corpuscular theory. But that lasted only around a century, because in 1801, a new scientist called Thomas Young proved that light had to be waves. So this guy, in 1801, did an experiment where he played with light in something called the double slit experiment. And with it, he proved that light underwent diffraction and interference. And if you remember, diffraction and interference are behaviors that are only of waves. Tennis balls don't have interference and they don't have diffraction. So Thomas Young proved that light had to be a wave. So for the following 100 years, everyone believed that light was a wave. But in around 1905, a guy that you're all pretty familiar with, Albert Einstein, came back and he did his experiments that proved something he called the photoelectric effect. And this effect is so important that it actually gave Albert Einstein his first Nobel Prize. And what he proved is that light was not only a wave, but also a particle. So with the photoelectric effect, he proved that light was both. This is called the particle-wave duality. And that's what we talk about now, particle-wave duality. So it's a pretty weird thing, it doesn't make that much sense, but light can behave as a wave, so it can undergo interference and diffraction, but it also behaves as a particle. And you can isolate an individual particle of light called photon. So before they were called corpuscles, now the particle of light is called a photon. So light is just a very regular name to call the electromagnetic spectrum. So actually what we're talking about is all of the electromagnetic waves. And that is a whole spectrum. That means that there are waves of every single frequency in the electromagnetic spectrum, and we as humans have given them different names. So here I'm going to write them down in an order of increasing energy. So I'm going to put here the electromagnetic wave with the least energy, and at the other end, the electromagnetic wave with the most energy. Okay, so here they are, the 7 categories of electromagnetic waves in order of increasing energy. So in this direction, energy increases. So the one with the lowest energy is called radio waves. You've heard about radio waves. They give us radio, like music. They give us Wi-Fi, data networks, even TV, right? Then we have microwaves. Microwaves are the ones that you have at home and that you use to cook food. They can only heat up water. That's the only thing they can do at this level of energy. Then we have infrared light. You've heard about infrared light, you've probably seen it. It's used in photography, and it's just red light. We can see some of the red light, but there's some of it that we can't see. Then comes the visible spectrum. This includes all of the colors that the human eye can see. At the least frequency, we have here red color. We have all the colors of the rainbow, and here at the end, we have violet. After visible light, we have ultraviolet rays. These are the ones that come to us from the sun and that can give us cancer. So from visible light upwards, this side of the electromagnetic spectrum can actually give you cancer, because these rays have so much energy that they can ionize, they can take an electron from your body's atoms, damage its DNA, and create cancer. So we have to take care of ultraviolet rays, X-rays, and gamma rays. X-rays are the ones that we use when we go and get radiographies at the doctor's office. So they just radiate you with X-rays. Usually it's okay if you only get 1 or 2 X-rays a year, but if you start getting more and more, it can increase your chances of developing cancer. And finally, we have gamma rays. Gamma rays have so much energy that they're actually used in radiotherapy to kill cancer, but they can also cause cancer around the area. A point here, microwaves are down here. They are even less likely of causing cancer than visible light. So if you look at your light bulb, it's more probable to get cancer than if you look at your microwave. So next time your mom or your aunt tells you, get away from the microwave oven, that can give you cancer, they're lying. It's not true. Okay, so why do these have more energy than these? That's because they have a greater frequency. So in this spectrum, we also have frequency increasing in this direction. Frequency is how many wave peaks there are per second. So if you have a wave that looks like this, it has a lot of peaks and it reaches you, it's going to do a lot more damage than if you're hit by a wave that looks like this, right? Because there's just less energy in it that is going to hit you. But we have our equation that we can't forget. That is the equation for waves, velocity equals wavelength times frequency. In the case of electromagnetic waves, we're going to see that what unites them all together is that they all have the same velocity that we usually call the speed of light. I'm going to put it here because it's really important. The speed of light is called c, and it's equal to 3 times 10 to the 8 meters per second. That's the same as saying 300,000 kilometers per second. It's the fastest speed possible in our universe. So if you change in this equation the speed of light, you can see that if you solve for the wavelength is going to be inversely proportional to the frequency, right? Because we pass the frequency to divide. So when frequency is increasing to the right, that means that the wavelength is decreasing to the right. So wavelength actually increases in the opposite direction. So wavelength goes in this direction. Also, this speed of light should actually be called the speed of electromagnetic waves. That would be more accurate because it's not just the speed of visible light, it's the speed of all electromagnetic waves in the spectrum. Okay, so the wavelength. So let's compare a little bit. We have the wavelength of radio waves, which is around 30,000 meters or 30 kilometers. So the wavelengths here, radio is 30 kilometers. That means that for it to have a peak and a valley and come back, it takes 30 kilometers. It can cross a whole town, basically, right? At the other end of the spectrum, we have gamma rays. The wavelength of gamma rays is 3 times 10 to the negative 12 meters. So 3 times 10 to the negative 12 meters. As you know, that is 0.0000000000003, I think, meters. That means that when here you could cross a whole town with just one wavelength. Here you need to have trillions of waves to fit them in a centimeter. Then we have the colors. Red has a longer wavelength. Nano means times 10 to the negative 9 meters. And violet, we have 400 nanometers. If something lies between 400 and 750 nanometers, we can see it with our eyes. Something in the middle, maybe green, could be 500 or 550 nanometers. Every color has its own independent wavelength. Something else I want to mention is the property of polarization of light. Polarization. So I'm going to write that up here. So we had previously learned that while sound was a longitudinal wave, light is a transverse wave. So when we answer the question, what is light, we also need to mention that it's a transverse wave. That means that it oscillates perpendicular to the direction of propagation of the wave. So that has a property that means that we can actually polarize or filter this light. So imagine you have a filter that looks something like jail. So it has bars and it has places where the light could pass through. Light waves can oscillate up and down, or they can oscillate side to side, or they can oscillate in diagonal. But if the holes are up and down only, if sunlight comes in and wants to go by, but it's oscillating side to side, it's going to hit the jail cell and it's not going to be able to pass. So basically, on one side of the Polaroid, you're going to have light oscillating up and down, and diagonal, in another diagonal, right and left, all of these possible planes of oscillation. But once they pass through the Polaroid, only the ones that were up and down will survive. So those were this one and this one. All of these were absorbed or hit the Polaroid and didn't pass by. So when you hear about Polaroid glasses, what that means is that you have tiny cells through which light could pass through your eyes, and it's only letting one direction of oscillation pass through your eyes. So that's why you see everything darker when you have polarized glasses. Now, because light is a wave, it also undergoes the other two wave behaviors, reflection and refraction. So let's see how that looks. So reflection is what happens when light hits a mirror. And light comes towards the mirror and hits it at an angle. So if you remember from our class on wave behaviors, we can determine the normal to the surface, and the rule for refraction is that the angle at which the light hits with respect to the normal will be exactly the same as the angle with which it reflects. So we can find here the angle of incidence, which is here, between the light ray and the normal. And so when the light bounces back, it has to have the same angle of reflection. What you need to remember is just the law of reflection states that the angle of incidence has to be equal to the angle of reflection, always. That's it for reflection. Now let's look at refraction. Refraction is the bending of light rays that occurs when light passes from one medium to another. So suppose we have a barrier and we have a medium 1 on top and a medium 2 on the bottom. So this can be, for example, air, and this can be, for example, plastic. So if you have a light ray that comes and hits the medium, again, we need to draw our normal with respect to the surface, or the barrier in this case. The light ray is going to bend such that it's closer to the medium if it changes to plastic. So this angle before, which used to be about 30, might now become about 15. So we have an angle here, the angle of incidence, or we can also call it angle 1 because it's in medium 1. And here we call it angle 2. And what determines those angles? It depends on which material it's coming from and which material it's going towards. So that is defined by a new term called index of refraction, given the letter N. So every material, every medium has its own index of refraction. The most common ones, for example, are an N for air, which is 1. The N for plastic is 1.5. And N for water is 1.4. So if you get a material that's not within these three, they will always tell you what's the index of refraction. And how does the index of refraction relate to the angle? Well, there's something called Snell's law, which gives us that relationship. Here it is. So the angle of the first one is theta 1, in this case, this one. And the N1 is the N of the medium. So in this example, this would be N1 is in air, so it would be 1. N2 is in plastic, so it would be 1.5. And then we would put theta 1 here, and we could find the theta 2 on the other side. So the index of refraction is proportional to how much it bends. The bigger the number, the more it's going to bend when it changes medium. And this also determines what happens to the speed. So of course, light can't travel as fast in plastic as it can in air. Actually, the value of 3 times 10 to the 8 meters per second is in a vacuum. If you're moving in air, it's a little slower. If light is moving in plastic, it's even slower. So how much slow? That is given by this other equation that the index of refraction can help us with. So if you know the index of refraction of air and of plastic, for example, and I tell you the speed at which it came in, you can give me the speed at which it came out in the other material. So these two laws will help you figure out both the angle and the speed of the ray when it undergoes refraction. In this bending of light, this refraction can help us understand a phenomenon known as dispersion that causes rainbows and prisms. So let's look a little bit into that. We know that there are colors, right? And we know that the light from the sun is white, or almost white, but we see things in different colors. So that's because white light is actually made of all the colors. So white light is what you get when you put all of the colors together. And you can test that by using a device called a prism. So prisms usually look like triangles, and they're made of this kind of plastic or glass. And what happens is, if you put in a ray of light, white light, it's going to bend a little bit. But because every color has its own frequency, every color is going to bend a little differently than the others. So red is actually the color that bends the least. So this will start happening. The red will bend a little bit as it comes in. The orange will bend a little more, the green a little more, the blue a little more, and the purple even more. And when they hit the second barrier and pass the air again, they're going to bend again. And again, red is going to have a bend that's a little bit less. Orange will bend even more. Green will bend more. Blue will bend more. And purple will bend the most. So this, you can recognize it probably as Pink Floyd's album cover. And what it actually is this piece of plastic, which if you look on the one side, you're going to see white light coming in. But if you look on the other side, you're going to see the rainbow of all of the colors. And if the plastic is clear, inside you can also see a rainbow. And that's what's happening. There is refraction here that causes the light to disperse into its different colors. And there's refraction again here that causes the light to disperse even more. This is exactly what causes rainbows. The raindrops act as prisms. So it looks something like this. As you probably know, rainbows happen when there's rain and there's sun. So what happens is that the light from the sun comes into the raindrop, it refracts a little bit, then here it reflects because there's something called total internal reflection that we might look at later. And when it bounces back, it'll refract again and cause the dispersion of light into the different colors. If you're standing down here on Earth, what you're going to see is not the light from the sun, but the light coming in every different color from the rainbow. Rainbows are an effect of refraction of light. And finally, why do we see things as different colors? So why, if there's only white light, we see this board as white, but my shirt is gray, for example? So that's because every object has different properties inside it that make it absorb some parts of the light, some wavelengths of light, and reflect other wavelengths of light. So if you have something that looks red, like let's say a red shirt, it looks red to your eyes because white light with all of the colors came in. Every single color except red was absorbed by the shirt, but red instead was the only color that came back to our eyes, making us perceive the shirt as red. So black things absorb all of the colors and don't reflect anything back at us. Since they absorb so many colors, that's why they get hotter. You know, when you wear a black shirt, you feel hotter because it's absorbing all of the colors. White instead reflects all of the colors, doesn't absorb anything. That's why it feels cooler. And it looks white because white is the sum of all of the colors. So that's how things have their color. If instead of giving white light to this shirt, you gave, for example, only purple light, what's going to happen is that the whole purple light will go in because it's not red light and there's nothing to reflect. This shirt only reflects red light, but if it's only purple, then it won't reflect anything and you'll see it as red. So if you're in a room that only has purple light and you have a red shirt, you will see your red shirt as black. And that's why we see things in different colors.